morning. First, I want to thank the organizer to give me the opportunity to present our work here in this nice conference. I'm really happy to be here with you. Today, I will tell you about our experiment in Paris that aimed to the accurate determination of the fine structure constant using atom interferometry. This work is done at Laboratoire Kastler, Brossel, with the collaboration of our PhD student Léo Morel and Yao Zibin and my colleague Pierre Cladet. So, the fine structure constant is one of the most important and most exciting fundamental constant of nature. He's a dimensionless constant, and I think that everybody knows this magic number. I hope that in my talk I will be able to ask two questions: why we need accurate value of alpha, and how we get accurate value using atom interferometry. So, the fine structure constant quantifies the strength of the electromagnetic interaction, and then it appears in many fields of physics, and thus it has been measured by different methods. For example, here, by measuring the transition frequency of the muonium ground state, hyperfine splitting, or from the measurement of the Van Clipsing constant, which is a constant of quantum Hall effect. But since the last 4th year, the most accurate determination of alpha comes from only two methods, from the comparison between the theory and experiment of anomalous magnetic moment of the electron, or from the recoil measurement. Such experiments are really hard and complex, and as you see here, we need about 12 years to improve the uncertainty by one order of magnitude. And today, I will tell you about this new value. Our main motivation here is to provide accurate value to calculate accurately the prediction of the standard model of the electron moment anomaly, because any deviation from the experimental value could be the signature of new physics beyond the standard model. So, let me say a few words on the current status of these two quantities. So, the anomalous magnetic moment of the electron is the deviation of the G factor of the prediction of Dirac prediction of the G factor of the electron. This deviation is about 1 per 1,000. It has been first observed by Quotient in 1947, and the first and is due to the effect of the vacuum fluctuation and polarization that modify the interaction of the electron with a magnetic field. And the first calculation of this effect has been done by Schwinger 2 years later, and it corresponds to one photon loop QD, which is described by this Feynman diagram. These two experiments, the work of Schwinger and the experiment made by Quotient Fuller, marks the birth of quantum electrodynamics. Today, the predicted value, the prediction of the standard model of this anomaly account for three contributions: the hadronic and weak interaction, and the dominant term comes from the QD, and is expressed as a power series of alpha, and these coefficients depend on the virtual particle involved in the interaction process with the vacuum. These coefficients are calculated up to the 5th order only by, I think, one group in the world, and the technique, they use the Feynman technique, and as you see here, we need more than 12 diagram Feynman to calculate this fifth order. And currently, the uncertainty on the value predicted by the standard model is limited by the knowledge of the fine structure constant. The QD term, the fifth order QD term, the contribution, and the hadronic term are more than one order of magnitude less. This quantity, the anomalous magnetic moment of the electron, is also measured experimentally by a group of Gabriel C. at Harvard by using single electron in pinning trap submitted to a magnetic field, and they measure directly this anormal frequency, which is the difference between spin and cyclotron frequency, and this transition frequency, the cyclotron frequency. And this measurement is done by using quantum jump spectroscopy. They achieve in 2008 a relative uncertainty of 0.22 ppt, and they expect in the next few years an improvement by one order of magnetic. They are starting measurement with a new experimental setup where they perform better control of electron motion, reduction of magnetic gradient, and they also expect to do the measurement of cyclotron and spin frequencies in nearly simultaneously. So, but the main motivation of all these works is to explain the Mayan puzzle. Namely, this persistent discrepancy between the predicted value of the anomalous magnetic moment of the muon and the experimental value. This discrepancy has been confirmed recently with a new measurement made by the Mayan G-2 collaboration, and also there was an important benchmark of the theory published in this paper. So, if this discrepancy is due to a new physics beyond the standard model, it should be observed on the electron. And using a simple and naive scaling, we can evaluate the effect on the electron that scale as the ratio between the electron mass and muon mass. And as you know, the muon mass is about 200 larger than the electron mass. This effect is too small on the electron, is about 610 to the minus 14. And currently, the uncertainty on this is about 510 to the minus 13. We need to improve all this experiment by one order of magnitude. So let me now switch to Paris experiment. How the starting point in our experiment is this relationship between Rydberg constant and the fine structure constant. From this relationship, we did use alpha from all these terms. Well, all these terms are known with good accuracy, and currently the value of alpha is limited by the ratio H over M between the Planck constant and the atomic mass. And this ratio could be deduced from the measurement of the recoil, atomic recoil. You know that one atom absorbs a photon, get the energy, but also the photon momenta, and the recoil by this velocity, where k is the wave vector. This recoil is too small, is about 6 millimeters per second for rubidium and 3.5 millimeters for cesium. There are only two groups in the world working on this on this experiment. So the principle of our experiment is really simple. We need two ingredients. The first one is a way to transfer to the atom a large number of photon momenta. For that, we use the technique of Bloch oscillation in accelerated optical lattice, and we are able to transfer more than 1,000 recoil velocity to photon momenta to the atoms. And the second ingredient is a Doppler atomic interferometer that allows us to measure precisely the induced Doppler shift. And in this case, the sensitivity on the recoil measurement depends on the sensitivity of our atom interferometer divided by the number of recoil transmitted to the atom. Here is the scheme of our the sequence of our atom interferometer. We use 2 pairs of p/2 pulse. Each pair induces a Raman transition between the 2 hyperfine levels of the rubidium ground state. The first pair creates a coherent superposition between these 2 states, and the 2 wave packets are separated thanks to the recoil transmitted to the atom that performs the transition. Then second pair, we put the 2 atoms in the same internal state. Then we apply a Bloch pulse in order to transfer to both wave packets a large number of photon momenta. And finally, we close our interferometer using a second pair of pi/2 pulse. And finally, we measure the number of atoms in each internal state, and the probability to find atom in F equal to depend on the delta phi, which is the phase difference between the 2 arms of the interferometer. This phase difference could be simply calculated using Feynman path integral, and we show that the sensitivity of interferometer depends on the mean velocity between the 2 wave packets and the separation between the 2 arms of the atom interferometry. More precisely, this sensitivity depends on the number of recoil transferred to the atom and the distance between the 2 wave packets, where r is the spacing time between the 2 p/2 pulse. To probe this atomic phase, we scan the phase of the frequency of the we scan the frequency of the Raman beam during this second pair of p/2 pulse. So this is the simple of the experiment. We produce a cold atom source here, about 10.8 atom with a temperature of 410 microkelvin, and then we use our atom elevator to transport atom to this area where we control perfectly the magnetic field. And then during the free fall of the atom, we apply our measurement sequence, which consists on the 2 pair of p/2 plus the coherent acceleration. And finally, we measure the number of atoms in each internal state to get the probability. So here I show you a typical spectra with this parameter. We are able to determine the frequency that compensates this term with an uncertainty of 50 millihertz. This corresponds to a sensitivity to recoil velocity of about 20 nanometers, or in other terms, to a relative uncertainty on h/m of 310 to the -9 in 1 minute, which is the time needed to record these spectra. We are limited, we're still limited, as we show you here, by the vibration. We don't yet achieve the standard quantum standard limit. we have a really stable and reliable setup, and we are able to run the experiment without any human intervention. For example, here I show you a set of data taken during a week, and we achieve a relative uncertainty on alpha of 4 × 10⁻11 on 48-hour integration time. With this really good statistical uncertainty, we was able to make measurement by changing many parameters like the duration of the Ramsey, number of Bloch, number of recoil momenta transferred of the atom, or the duration of the current acceleration. We also study many experimental effects, systematic effect by experimentally. So here I show you our error budget. The dominant effect comes from the GUI phase that I will explain in my next slide. And with respect of our last measurement, previous measurement down in 2011, we pointed out 3 new systematic effects. One due to the wavefront distortion, one due to the residual Raman phase shift, which is due to expansion of the atomic cloud during the measurement sequence, and more technical effect due to a phase shift observed in the phase and PLL used to phase lock our 2 laser Raman. In fact, as we showed you before, the atomic phase, the h/m is deduced from the atomic phase. And for that, we need to deduce, we need to measure the k vector of the 2 lasers, Raman laser and Bloch laser. And in the wonderful world, if we had a plane wave, it's easy to measure. We need only to measure frequency. But unfortunately, in the true life, we have at best a Gaussian beam, and we have to take account the correction due to this effect. And in this case, this correction could be, in the case of the GUI phase, this correction could be calculated exactly, is due in fact to the dispersion of the wave vector. It depends on the width of the laser, the size of the cloud, and the curvature of the wavefront. Considering our experimental parameter, where this is still the most important contribution, and the effect is about this amount. We also discover another effect due to the local and short-scale fluctuation of laser intensity. This, using a paraxial approximation, we can show that this effect induces additional correction that depend on the Laplacian of the laser intensity. And as the probability to transfer recoil to the atom, or in other terms, the survival, the probability during the Bloch oscillation depend also to the intensity. There a correlation between this correction and this probability. We observed this experimentally, and we took 2 years to understand really the origin of this effect. And now we are able to mitigate this effect by maintaining the probability close to 1. In this case, this effect average, and this contribution is now about 210 to the minus. The uncertainty on this effect is 210 to the minus 11. This is our new value. We obtain a value with a relative uncertainty of 810 to the minus 11 with good statistic. New systematic effect has been considered, and we provide a new value of anomalous magnetic moment it is more in agreement with the experimental one. We consolidate the test of the fifth order contribution and hadronic and tau contribution, and we need to improve by factor 4 to see for the weak effect of the weak interaction. Unfortunately, or fortunately, I don't know, we have a discrepancy of about 5.4 sigma with respect of the measurement down by group of Holger Müller in Berkeley with cesium, and we need to explain. Okay, we need to explain this discrepancy is very important. So. And as in this diagram, I show the contribution of different contribution to delta AE, okay? And we see here I put in green the expected this value here, and as we see here, we for the first time the contribution of H over M is close to this value. But of course, to explain this discrepancy, we need to reduce this, both this effect and also the experimental value of AE, which is still the dominant contribution. So, as you know, since 2019, we are defined a new assay system of unit, which is based on fundamental constant, and in particular, the kilogram is now defined by fixing the Planck constant. And our experiment that measures the ratio H over M is allowed to the mise en pratique of the kilogram at the atomic scale. And this measurement is the most accurate measurement of the atomic mass in the new SI. Also, the fine structure constant play an important role in adjustment of fundamental physical constant in the new assay. And for example, epsilon 0 and mu 0 are not longer fixed, and their value depend now of the fine structure constant because all other constants are fixed now. And this is a new value of mu 0, not exactly 4p 10 to the minus 7. More generally, our determination improves the uncertainty of 90 fundamental constants among the 54 listed by the CODATA. So, when I come back to our error budget, and important systematic effects are exacerbated by transverse motion of the atom. And then to mitigate this effect, we need to use ultra-cold and dense atom. And these, the drawback that these need longer production time, which affect the statistic, and also a detrimental phase shift due to atom interaction. We are currently doing a new measurement using Bloch, using Bose-Einstein condensate. We produce our condense about 200,000 atoms in 3 and 4 seconds in all optical trap. And we see here we have a stable also and robust setup, but we have a statistical uncertainty is 1 order less than with molasses. This is due to vibration. We are working in fact, we move experimental to another experimental room where the vibration are more important, and we are working to reduce this statistical uncertainty. So we spent the last 6 months to measure the phase shift due to atomic interaction by using this simple scheme, theta p, theta pulse, where theta is the pulse area. The idea is to create an imbalance between the two arms of the interferometer. Our idea here is to find a robust way to evaluate the systematic effect due to atom interaction. And we develop also two models which that agree perfectly with our experimental data without any adjustment. And here I show you the total phase shift at the output interferometer as a function of the release time of condensate. We switch the atom interferometer TF later after switching off the dipolar trap. And you see that this effect of interaction vanish, and we are able to evaluate this effect correctly. We also measured the phase gradient due to mutual interaction along this vertical direction, and as you see, our model is in good agreement. Now we have a tool to accurately evaluate this systematic effect. So now our motivation, of course, is to explain this large discrepancy. As I said before, measurement with Bose-Einstein is in progress. We also plan to measure the recoil velocity of the isotope 85 of the rubidium, and we are now building a new experimental setup with larger interaction area. We plan to use a large momentum beam splitter to improve the sensitivity and the statistic, and also larger beam to reduce this GUI phase. Our target is to reduce the contribution of H over M at this level, and of course, before we should explain both these discrepancy. Here, people involved in this experiment, I thank my small group, and I also thank the funding agency, and thank you for your attention.
Well, thank you, Saida, for this beautiful talk. It certainly is a remarkable test of QED that you can add up 12,600 or so Feynman diagrams and still end up with something significant at the end. So, questions?
Okay, thank you very much for your nice talk. One misunderstand, one fact that has been neglected from many people is that interferometry determination alpha actually strongly depend on QED calculation, because you need to very precise value of Ripple constant and the electron mass in U. Mm-hmm. Okay. Now, if you want to reduce the factor uncertain by a factor of 10 from 81 to 8, the electron mass in U should be reduced. The current uncertainty is about 29 ppt. Okay, so that involves a QED calculation because it depends on the G factor of hydrogen like carbon 12.
So I agree.
Okay, yeah, that's maybe fine, but you still need to use a penny trap to remeasure, to improve the mass of ME in U. So this is one thing, because otherwise it will be a bottleneck. You reduce your measurement, the mass by a factor of 10, then you still cannot determine alpha. Okay. Another thing is that the Ripple constant, so far it's like 3 ppt, but it's still controversial at last 2 digits. Okay. So of course it determined from hydrogen, 1s, 2s, 1s, 3s. It's still controversial. So I think it's a good time to revisit R and the QED calculation for and the measurement for determination for electron mass in U before you can further improve your alpha to like 10 ppt. Okay, because yeah.
I agree totally with you.
Yeah.
I agree because our job is to measure H over M, but to converge to
Yeah.
a good value of alpha. We are mini group in different research field working on that.
Yeah.
And we, for example, yesterday we discussed it with Edmond and people that are involved in mass measurement. Also, we had the discussion with Klaus Blount,
Yeah, Klaus
and
Blount, yeah.
they also said it is possible to obtain for rubidium, relative rubidium mass uncertainty less 2 to minus 11.
Yeah.
And
Great.
for Rydberg constant, I think we are confident to 10 to the minus 12.
Okay.
Okay, I think.
Yeah, that's promising.
Yeah, promising.
Very cool.
But I agree with you, is a common job, and every research domain will make effort to converge to this perfectly.
Yeah, I'll come to you in just a minute. But first, questions from students. Let's give students a chance to jump in here.
Students, yeah.
Hello. I was interested in your slide about the elevator, and you said that you had a perfect magnetic field in there. Could you talk a little bit how you achieved
Which
that?
one? This one?
About halfway through your presentation. The atom elevator.
Oops. Well, it's better to do it with, I think, with computer. Oops. Oh, sorry. Okay.
Yeah, this slide.
Okay.
Oh, yeah, unfortunately, it didn't come up.
Okay. Yeah. Sorry.
So my question was just about, you said you had a perfect magnetic field in this region?
No, never perfect, of
Yeah.
course. 50 nano Gauss, and we measure it by doing a co-propagating Raman transition. Okay, we measure at different position, and we get the profile of the magnetic field. Of course, never is perfect in experiment, yeah.
So then
Nothing is perfect, sorry.
So then my follow-up question is, do you quantify this in your systematic effects? Because I wasn't sure I saw it listed in that table you had, sorry. Then you have to go to another slide, I think.
Okay, so the systematic effect. Okay, I go there. It's not work. What's your question about systematic effect? The effect of magnetic field, you mean?
Yeah, I was just wondering, so you say that you measure this, do you then quantify this as part of your systematic
of course,
effects?
but it's so negligible. Okay.
Okay,
In
so
fact, we quantify also all level shift, magnetic Zeeman level shift, light shift, and also. But I probably don't put it because it's negligible. And the protocol of experiment is less complicated, and we eliminate many level shift by combining different configuration of the experiment.
We'll give Bill the last word.
thank you very much.
Other question? Yeah.
A few years ago, I encountered a mathematician named Sir Michael Atiyah, and he claimed that he had proved the Raman hypothesis, which was a controversial claim, but along the way to proving it, somehow or other he was able to calculate what the fine structure constant was. Now I said, well, that's really interesting. It'll be great, you know, when our community gets a better value of the fine structure constant, we'll see whether you're right. And he said, no. This is the value of the fine structure constant, according my calculation shows it. Well, you know, I've been around long enough that I've heard a lot of people say that kind of thing. What I'm really wondering is, have you paid any attention to what this Fields medalist calculated for the fine structure constant? And can you say anything about whether he's right or wrong?
To be honest, Bill, in fact, I receive each week a letter from guys with complicated calculation. Really,
Exactly.
I have these in my office.
But how many of them are Fields medalists?
But I never read this letter. But if you want, I can do it and give you an answer by email.
Okay.
But really, I have
Great question.
Wonderful.
And we'll leave that question dangling as we proceed to the next talk. First mention that these are both this talk and the following one are chosen as hot topics talks. So I hope you enjoyed this one, and it will be followed by a talk by Shimon Kolkovitz.